Hello, everyone. Welcome to the IFIMAC Day 2025. We are going to start with a little bit of delay, but there are always technical issues that we have to fix. Even if we are using this room many, many times, there is always some issues. I would like to start thanking both María Ángeles Martín Cabrejas, the Vice Rector of Scientific Policy of UAM, and José Luis Pau, the Vice Dean of Research of the Faculty of Science, for being with us in this opening for this important day for IFIMAC. And as we are running out of time, I would simply pass the floor to María Ángeles. Thank you.
Okay. Good morning, everyone. As a Vice Rector for Scientific Policy, it's a great pleasure to welcome you all at IFIMAC Day 2025. We are delighted to gather here today to celebrate the vibrant scientific community that makes IFIMAC such a dynamic and inspiring research environment. This day is dedicated to show the excellence, the diversity, and the creativity of our researchers, from those who have recently joined us and to those whose outstanding contributions have been recognized at national and international level. I think it is also a moment to reflect on the collective achievement and also to look ahead to the exciting challenges and opportunities that lie before us. We began with an overview of the current state of IFIMAC presented by the director, Professor Rubén Pérez, followed by, I think, an interesting session highlighting the work of young researchers who have recently become part of our center, of the IFIMAC. And I think this fresh perspective and also innovative approaches are already enriching our scientific landscape. Later in the morning, we have the pleasure, we will honor the IFIMAC researchers who have received prestigious prizes. I think their work means the excellence and impact of their work research. We are really proud to celebrate their achievement with all of you. Through the day, I do hope you will take the opportunity to engage with colleagues, explore new ideas, enjoy the poster session, and informal discussion over coffee and lunch. Finally, I would like to thank you for being here and for your continued commitment with the IFIMAC community. So let's make this an inspiring day. So enjoy the session. Thank you very much.
Thank you. José Luis.
For me to be here and participate in this opening session on behalf of the faculty. I'd like to thank the director of IFIMAC and the members of the steering committee for the kind invitation to be part of this welcome panel. I guess that this annual gathering is always a valuable opportunity for the Institute to reflect on the progress made by the different working groups, to share insights and prospects for the future, to define new plans and new ideas for the Institute that would be valuable for all of us at the end of the university. It is a moment to celebrate achievement, strengthen connections, and look ahead with ambition. This has been a particularly significant year for IFIMAC, marked by its formal constitution as a foundation. These milestones really opens the door to new opportunities and challenges. I'm confident that it will further enhance the Institute's capacity to lead and innovate. The national and international impact of IFIMAC is undeniable, as are the fruitful collaborations that emerge from its dynamic research environment. IFIMAC, I think, is an example of multidisciplinarity, multidisciplinary approach in research, combining physics, chemistry, material science, and biology, and cutting-edge topics like advanced materials, nanophysics, quantum optics, soft matter, or biophysics. So I think that IFIMAC is clearly an example for our campus of excellence. I declare my admiration for the dedication that all of you have on the pursuit of science and to break frontiers of knowledge and advances beyond what is established. And well, I also like to thank the contribution to outreach and dissemination activities that you carried out in the Institute. An example is the celebration of the International Year of Quantum Science and Technology, which is a proof of your role in promoting science within and beyond the academia. Let me conclude by expressing my admiration for the whole community, entire community, that results in prizes and awards, like the ones honoring today, in hands of Professor García Vidal and Professor Gómez-Navarro by the Spanish Royal Society of Physics and Fundación BBVA. And I wish you a productive and stimulating IFIMAC Day and continued success in all your endeavors.
Thank you. And with this, I think we finish the opening ceremony. And we really thank you for your words and for your presence in this opening of IFIMAC Day. I think it's really important for us to have the collaboration of.
So thank you very much, Ruben, for the update. It is really my pleasure to chair this session because it is, as Ruben said, one of IFIMAC commitments is to keep incorporating into the Institute young and new talent. And in this session, we will have two very good examples of this commitment. First of all, we will have Miguel Bello, and then we will have Iolanda di Bernardo. Miguel recently joined IFIMAC since February, and he is the one of the two persons awarded with the IFIMAC Junior Leadership Award. Miguel graduated in physics here in Madrid at the Complutense. Then he moved here to the Universidad Autónoma de Madrid for his master and did his PhD under the supervision of Gloria Platero at the Instituto de Ciencias de Materiales de Madrid. After that, he moved to Germany. He worked there for 5 years at the Ignacio Ciracs Group, where basically he has been working on topological systems, both quantum meters and dynamics, many-body dynamics. And he will tell us about his work right now. So, Miguel, welcome and thank you.
Okay, thank you, Cristina. Yeah, so first of all, I would like to thank the directors of IFIMAC for organizing this day and also giving me the opportunity to talk about my work. So yeah, the title of the talk is Quantum Optics in the Many-Body Regime, Challenges and Opportunities. But I should rather say just challenges, because for the moment I don't have very good ideas of what to do then with this, and it's in general theoretically very challenging. And the plan of the talk is the following one. First, I will tell you a bit about the path that quantum optics has followed in over the course of the last decades, and I will exemplify a bit the improvements that have happened with some example taken from work that we recently finished. And then I will tell you what is this big challenge of computing quantum dynamics for these hybrid-like matter systems, and describe a little bit what are the tools that we have to tackle this problem when we are looking at few body dynamics. And one possible, or let's say, set of tools to tackle this many-body problem. And then I won't have time to go into the details, but I would also like to mention some other directions that I'm also working on. All right. So right from the beginning, quantum optics is already quite old, and initially the motivation was to understand nature, fundamental questions like how does light and matter interact? For example, atoms, how do they emit spontaneously photons? And slowly but steadily, we realized that all this knowledge allows us to control nature. No? And one paradigmatic example is the following one. Let's assume that you have an atom inside a cavity. So the atom, if it was in free space, would have some decay rate. But by tuning or placing it inside this cavity, which is a way to control the environment of the atom, we can enhance its decay rate. No? So if the free decay would be given by these gray curves, so this is the probability to find the atom in the excited state, then we can, there is this phenomena called Purcell enhancement, and we can enhance the decay rate. And if we obtain or achieve even stronger coupling between the atom and light inside this cavity, we can produce altogether very different dynamics, no? Such as these Rabi oscillations. And where we are now. So now scientists can fabricate very complicated devices. This is one example. So what you are seeing here in this microphotography is a superconducting circuit that acts like superconducting metamaterial, and it's essentially made of resonators that are coupled capacitively together. Then these other pieces are qubits, artificial qubits, transmons. So other resonators that have some harmonicity that can be controlled. And theoretically, this system would be modeled as an array of cavities, and each cavity has an atom, no? And we can control all the couplings between the cavities, the strength of the coupling to some degree between the transmon qubits and the resonators. So it is a very exciting time because the complexity of the devices that we can fabricate has increased a lot. And I mean, in this map, I'm kind of showing a measure of this complexity, which would be the number of photonic modes that you can engineer and the number of emitters that you can couple to these modes. So there are different platforms. Superconducting circuits is one of the most well-developed, but there are also quantum dots in semiconductor structures like photonic crystals, also ultra-cold atoms trapped in optical lattices, or vacancy centers in silicon. And yeah, I was saying that it's very exciting because, of course, with these devices, you can explore new physics, reach novel regimes that were not available with previous experiments. But also for theoreticians, it is a challenge to be able to model these systems and to understand them. So as an example, I want to tell you some of the work that we did with the experimental group of Jelena Vukovic at Stanford. And I also want to highlight the role played by Daniel Lukin, who was a postdoc in Jelena's group, and Bennett Wind, who was a PhD student in Ignacio's group while I was there. So they are able to fabricate this kind of structure made in silicon carbide. So silicon carbide is like diamond. It's an insulator that has the structure, the lattice of diamond, and half of the atoms are replaced by silicon. And if you have a vacancy, so in the place of a silicon atom you have nothing, then somehow this is negatively charged. You have an electron around here that has some energy levels that lie in the gap of the material. And for us, this is just like another atom or quantum emitter or two-level system. For me, all these things are the same, essentially. And it interacts with light in the optical range. So yeah, with nanolithography techniques, they can fabricate this ring resonator. So this is like a dome-shaped disc. And this would be a very simple theoretical model to understand the behavior of this system. So neglecting all, external decay and defacing channels, like, of course, light can escape from the resonator and from the atom, from the qubit, and so on. But let's just look at the coherent interaction between our emitter, our vacancy, and the modes in the resonator. No? So the resonator has essentially two modes that have a frequency in the range of the transition frequency of the vacancy. And this are the clockwise and counterclockwise modes. And they also are able to place this waveguide, a non-optical fiber, close to the resonator, such that the clockwise light couples to one end of the fiber, and the counterclockwise light can couple out in the other direction. So the model would be, okay, we have two modes with some frequency. These two modes can be coupled to each other through some backscattering process. So light can change direction, maybe. Then we have the two-level system, and this sigma is just the ladder operator for the vacancy. And there is some coupling between which is, for simplicity, of the James Cummings type between the vacancy and the two modes of the resonator. And crucially, this coupling depends on the phase, which would be the phase which would be related to the point which you proximitize this nanofiber. So schematically, I like to represent this Hamiltonian with this graph. We have two nodes that correspond to the clockwise and counterclockwise of the cavity, and another node would be the qubit. These have different frequencies, so that's why I colored them differently. And then we have these couplings, and these arrows here indicate that there is some phase. So the excitation gets a phase when it jumps goes from the one mode to the emitter, and gets another phase when it goes to the other one. And you can very easily realize that this system is chiral, because if I exchange the two modes, A and B, then the phases are the opposite ones. And there are some physical consequences for this. So they did an experiment in which they measured the photon statistics. So essentially, what is the probability to get a photon either in this configuration after some time tau, so you detect a photon. Essentially, they measure the second degree correlation function, which tells you what is the probability to get a photon after having detected another photon with some delay time tau. And there are different configurations, either on the same channel or in the opposite channels. And because since the system is chiral, what happens is that the light that you get out of each port has different statistics. So on one port, you have some anti-bunching. In the other one, you have some bunching. And if you look at the cross correlations, this is asymmetric because it's telling you that it's not the same detecting one photon on the left port and then waiting some time tau and detecting another one on the right one, or the opposite process. But okay, what happens if you make a very good cavity such that there is no backscattering between the modes? If you look at the system, you may think, oh, the system is clearly chiral, no? Like the emitter is, it would not be chiral if it's placed symmetrically, no? But this is like a very different thing to difficult thing to achieve. But in fact, if you make the cavity so well such that there is no backscattering, actually you can gauge away the phases, right? Because the only quantity that is gauged invariant actually is the total phase accumulated in a cycle in these graphs. So here, I mean, this is reminiscent of the Aranov-Bohm effect, if any one of you has heard about it. So yeah, with this gauge transformation, we get rid of the phases and we obtain a system that is symmetric under the permutation of A and B modes. And now the consequence is that the second degree correlation function is symmetric and all of them are the same. But we can think of or look at more complicated systems. So what happens if you have now two emitters and you don't have this backscattering? You may think, oh, now we have this loop, so there is some phase, the system is chiral, but actually not, because you can exchange the two modes and also exchange the two emitters, and again, you obtain the same system. So this would not show this asymmetry in the G2 functions. Of course, one difference is, or a completely different situation is, if these two emitters are not exactly identical, then you cannot exchange them. No? And this could be because they have different transition frequencies, or because they couple with different strengths to the fields in the cavity. But now there are some things that some surprises. So for example, if you are in this situation where one of the emitter is coupled more strongly to the modes, but the two of them have the same frequency and is resonant with the cavity frequency, then numerically we observe that we have some symmetry, but we couldn't figure out which one it was. Also, it is very easy to analyze what would happen if you, instead of emitters, had two additional bosonic modes. This is just to make the system solvable, because then it would become like some quadratic Hamiltonian in terms of bosons. So, and in that case, one can also figure out a different symmetry. Essentially, you can create new modes combining these two that also satisfy bosonic statistics. This is not possible with spins. When you combine spins, you don't get more spins. And in a way, relates this chirality in the steady state with the interactions induced by the emitters. So, I mean, this was just to show that naively the system might look simple, but it is actually very difficult to understand. And then in the experiment, so this is a picture of the cavity, and with somehow when they couple molecules to this cavity, they are able to tune the resonant frequency of the modes. So they can do a sweep for several frequencies. And then when they fabricate these devices, they don't have a control over the placement of the vacancies, no? So different vacancies have slightly different transition frequencies. And this is what you are seeing here, no? For some frequencies, some of the emitters are active. For a different cavity frequency, some other ones are active. And we were able to model this system and realize that by tuning this, you can also tune the behavior of the second order correlation function and make it more or less asymmetric. So, I mean, this could potentially have some applications. Right. So going back to the big question, so why these hybrid light matter systems are difficult to study in the many-body regime? Well, if one looks at one particular model here, so this red lattice would be some photonic crystal, and these blue spheres would be some emitters. You have a local Hamiltonian, and you have some dynamics that you can study. And usually for local Hamiltonians, the entanglement grows linearly in time. And there are some, I mean, these have some implications, for the dynamics that you observe when you look at the system in this way. So the relevant timescale would be, for example, the coupling between the cavities. On the other hand, you can, if the coupling between the emitters and the photonic structure is very small, you can trace out the photonic structure in some cases. And what you get is some non-local description given by some master equation. So in this master equation, there is an effective Hamiltonian with some all-to-all interactions that are mediated by the modes in the environment. And you also get dissipative all-to-all interactions, right? And the fact that the system is non-local makes it very difficult to study, to tackle numerically, because entanglement now grows with time in a much faster way. And at some point, your numerical method is down because of this. So this is telling you that depending on the physics that you're interested in, you may reach different limitations. So there have been many works looking at the exact few body dynamics in these systems. There are many tools available. So some of them are listed here. There are spectral methods that exploit the translational invariance of the environment to compute what is the dynamics of excitations in the environment very quickly. There are also Langsos techniques that rewrite, for example, some complex photonic structure into a chain of connected modes, so effectively reducing the dimensionality of your problem to 1D. One can do green function computations. There are also some other tools, for example, drawing from engineering and classical electromagnetism. There is this tool called perfectly matched layers, which allow you to simplify your environment somehow. And people have looked at many different phenomena. So bound states, how these emitters can trap light around them, scattering. So how do these emitters scatter light and generate, for example, correlated states between the photons, phenomena such as super and subradiance. And overall, when we have exact methods, we can go beyond the Markovian approximation, which was this one, and look at what are the actual dynamics in your system. And here I just want to highlight a work that we are doing right now with Sergio Paniego and Alejandro González Tudela, in which we are trying to apply these few body techniques to similar problems of impurities, but instead of looking at emitters and photons, we are looking at a spin system. And this is interesting because naturally in these spin chains, this is it's an interacting environment itself, no? So photons in a photonic structure usually don't interact among each other, but in these spin models, or let's say models taken from traditional condensed matter theory, you have some interactions that can give rise to new behavior. And we are trying to compare both worlds, the world of quantum optics with the world of impurity models in condensed matter. Now, one possible set of tools that would allow us to tackle the many-body problem are variational methods. So briefly, what you do is, okay, the Hilbert space dimension explodes, increases exponentially with the number of particles that you are trying to understand. So let's reduce the set of states that we are looking at to some particular manifold parameterized by many fewer parameters than the whole Hilbert space. Then what you can do, very naive, okay, we have the Schrödinger equation that would tell us how the system evolved, and we can project it on this manifold. So if the Hamiltonian is telling me how the derivative of the state would evolve, would be at some specific time, and if I project it to the tangent plane of my manifold, I get some motion within the manifold, right? But there is a problem, and the problem is that if you do this naively, you may encounter or you realize that actually, depending on which Schrödinger equation, essentially here is the same equation just where I place the I on the other end, would give me different equations of motion. And why is that? Well, the reason is that the most general manifold that I can consider would be parameterized by real parameters. If I have some complex parameter, I can separate it into its real and imaginary part. So let's just work a very naive example. If this is my state, then I compute the tangent vectors. So what is the derivative of the state with respect to these two parameters? And I would get this one and this other one. And if I look at what are their duals, it would be given by these expressions here. So this means the dual of this vector is, okay, this one where that would act on a state, computing the overlap and then taking the real part. And now the projector essentially has this real part here. So now you can realize why, depending on where you place your eye, you may be computing the real thing of something different, and why this is not so trivial or easy to do. By the way, this example is a bit flawed because, I mean, no matter how I change these two parameters, I always get the same quantum state. This is just a complex constant, so it wouldn't change anything, but you get the idea of how this thing works. And okay, I just want to mention that there are people have looked at this and have come up with different kinds of variational families. Famous ones are, for example, tensor networks, where you express your coefficients in some basis. So, for example, let's say this is the Ising basis for a set of spins. You deconstruct or express these tensors into these much simpler tensor networks, where these ones are now tensors of a much smaller number of elements than the big one, no? So the ability, in a way, this is compressing all the information stored in these coefficients, and this compression is better or worse depending on what is the dimension that you allow for these virtual indices that are constructed. So in a way, you can make these ansatz more expressible or less by changing this bond dimension. You also have a different kind of ansatz based on neural networks. Here again, you have some complicated function that depends on many parameters, and you express it as some network with some activation functions. And for example, I could add more layers of nodes in this network, and in this way, I would be able to encode more information somehow in the network. But always, the idea is always to reduce the number of parameters describing the system, no? And in these two ansatz, you can see that this thing can be done somehow systematically. But there are other ansatz, such as Gaussian states, for example, which are very well understood states of bosonic and fermionic systems, and they are completely characterized by the first and second moment of the quadratures of the modes. These are fixed. Here I only have these many parameters, and that's it. I cannot increase them. No? So why should we consider them? Well, for a start, for example, tensor networks are very good whenever you have state that has low entanglement, because you can see the entanglement as the dimension that I have to keep here in the links to faithfully represent the state. But for example, this would only work for ground states of gapped Hamiltonians. If I have a system that is gapless, then the state wouldn't satisfy an area law of entanglement, and instead maybe a Gaussian state is a better approximation for the ground state. So yeah, different ansatz are tailored to study different regimes, different situations. And one of the work that we are doing now, together with Javier del Pino, who joined IFIMAC as a research fellow recently, as a Ramón y Cajal Fellow, is to create new ansatz based on the previous one, combining them in different ways. So we can just look at product states where I consider, for example, a matrix product state, a neural network state, whatever, for the emitters, and then a Gaussian state for the environment, for the photonic environment. Another possibility is to consider superpositions of these states. So, for example, coherent states are a basis, an overcomplete basis of the Hilbert space. So this means that if I keep adding Gaussian states, at some point I can represent any state of my bosonic system. And I can also look at correlated superpositions where I have a different Gaussian state depending on the state of my emitter. So there is a whole slew of possibilities that are open to explore and see in which situations they allow us to tackle these quantum many-body dynamics. And okay, I will finish now. Some other work that I've done is to look at what are the retardation effects, how they impact collective phenomena such as superradiance. So in this work, we investigated what happened when you couple emitters to a chiral waveguide, meaning that light can only propagate in one direction. This is essentially a cascaded quantum system. And this allowed us to do some, to go to the thermodynamic limit, which is really difficult. And as Cristina mentioned, most of my work so far was about topological systems, and I am still continuing this research line. My postdoc, Juan Zurita, who will present a poster this afternoon, so go check it. And yeah, this is all of it, and thank you for your attention.
So thank you very much, Miguel, for the clarity and talk. We have some time for questions, comments.
Thank you very much. Interesting for me. I am not expert in this, but I know that in spin waves in circles, there are so-called Vesperi gallery modes. In your optic coupled to the qubits, I understand. Is there some kind of these modes in which you have inserted kind of defect or impurity, just to explain it better for experimenters?
So if I had made the device with a pristine material, no, I just have these two whispering gallery modes by themselves, right? This is just a very high quality cavity. And then these vacancy couples, I think, to the transverse. So I don't remember the details. I think it couples to the transverse magnetic field of these modes. And then depending on its placement, you get stronger or weaker coupling. I don't know if this answers your question or what was.
That's sufficient for me, because I understand that without vacancy, it's Vesperi gallery modes. But my question was, still in the presence of vacancy plus quantum dot, is it still could be called this mode, which is scatters out of the defect, or it is just already different physics? That was my question.
No, it's the same, and actually the coupling is weak in this case. It's not so strong. So
okay, thank you.
So we have time for one more question. I strongly encourage young researchers, but no.
This is not young. No, just a simple question. At the beginning of the talk, you presented the example of, I think it's this silicon carbide color center. I understand it's a physical realization of what you are doing or not. I mean, for instance, I'm experimentally, we're interested in other, we investigate the color centers, nitrogen vacant, famous NV centers in diamond, etc., which is the same structure. So there are other color centers. My question is, what you have shown could be easily applicable to other color center in similar system, or is something specific that I missed that what you are?
No, I think in principle, no. The physics is the same for other materials and other color centers.
Yeah.
Of course, each color center will have a different energy level scheme, and maybe in some cases doing just a two-level approximation wouldn't be feasible, or I don't know. Also, this whole experiment is done at cryogenic temperatures because there is relaxation due to phonons of the structure and so on. So I don't know in other materials if they have enough life to stay in all these, like to observe all these physics. No, like every material would have like a slightly different energy landscape. And
you check it quantitatively, but in principle, it could be feasible if the numbers of the energies fits.
Yes. I'm aware that there are many other experiments where they also fabricate artificial qubits based on other color centers.
Okay, thank you very much.
So thank you very much, Miguel. I think we have to move on to the next talk.
Right.
So our next speaker will be Iolanda di Bernardo. She recently incorporated IFIMAC also as the Ramón y Cajal Fellow. Her expertise is on scanning-proof microscopies and photoemission spectroscopies. And I think she will tell us about his previous places. So I won't make any spoiler. Let's welcome Iolanda, and thank you very much.
Thank you, Cristina, and I would like to thank the organizers for giving me the chance to introduce myself and a bit of my work here in this occasion. In case you didn't guess from my accent yet, I'm Italian. I got my PhD from Sapienza, University of Rome. And then I moved around a bit. I spent a few years in Australia before coming back to Europe. I was in Autonoma for a bit, then I moved up the hill. I went to work at Imdana Nociencia, and now I'm back here at Autonoma as a Ramón y Cajal Fellow. And I'm definitely on the experimental side of condensed matter. And in particular, what I do now on a day-to-day basis is STM and STS, so scanning, tunneling, microscopy, and spectroscopy. But as a training, I'm a photoemission spectroscopy person, so I do a lot of RPS and a lot of XPS. Right now, I don't have neither a lamp nor an analyzer, so I rely on synchrotron radiation facilities to do my photoemission experiments, but my expertise is a bit the overlap of all of this. And while this is the instruments that I use, this is what I look at. As I said, I'm an experimentalist, so this is the only Hamiltonian that you will see now here. This is just the Hamiltonian for the electrons in any material once you freeze out the nuclei in the Born-Oppenheimer approximation. And in a normal, in the normal standard case, you would have a kinetic term and then an interaction term given by the potential. And you know that, as you all know, I guess, in the kinetic term, you have the creation and annihilation operator for the electrons, and then there's an overlap term in front of it. And then, of course, in the interaction term, you can have first neighbors, second neighbors, and all of that. In a normal material, the hopping parameter, which is the T that you see there, is much larger than the U, which is the potential that makes the electrons interact with each other. And that gives rise to a state where the electrons are free to move, sort of. So you have your standard metal or semiconductor. In strongly correlated materials, the opposite is true. So the interaction potential is much stronger than the kinetic energy of the electrons, which means that the electrons are not as free to move. And the Coulomb interaction between electrons is what dictates what happens to the electrons in the material. And this is what is at the basis of superconductivity, Mott insulating state, charge orders, and all these sort of funky systems. The specific work that I'm going to present to you today is work that I've done in collaboration with people that are in Melbourne and in Singapore. In particular, most of the experimental work was done by the now Dr. Liam Watson, which I co-supervised with Professor Michael Fura. Some of the experiments were performed in the labs of Professor Bent Weber in Singapore. And shout out to Michal, the guy whose name is Red Circle, for all the theory that you will see today. Both works came out this year, and both works are focused on tungsten ditelluride. Now, in the very remote case that some of you don't know what a transition metal dechalcogenide is, tungsten ditelluride is a member of the transition dechalcogenide family. Transition metal dechalcogenides are characterized by having a unit cell, which is the one that I'm depicting there. You have a transition metal layer, which is sandwiched between two chalcogen layers. And this specific transition metal dechalcogenide crystallizes in a structure that is known as the distorted 1T'. So compared to, for example, molybdenum disulfide, in moly disulfide, the molybdenum atoms are all equally spaced. In tungsten ditelluride, the tungsten basically form dimerized chains, and the chalcogen layers arrange in a zigzag fashion in the direction perpendicular to the plane. This means that if you were to look at the material from the top, and this is important for the following, you would have alternating rows of high and low chalcogens zigzagging. Now, this material, at the very beginning, was predicted to be a quantum spin-hole insulator, so a topological insulator, pretty much. And this is because the bands that you have at the Fermi level from tellurium and tungsten have different parity, so spin-orbit coupling would make them overlap, but because of the different parity, the crossing is avoided, and so you have the opening of a topological band gap and the formation of topological edge states. This was demonstrated as early as in 2017. This work is the group of Professor Mike Cromie at Berkeley. You can see here that they grew tungsten ditelluride via molecular beam epitaxy, and they looked at it with STM. So they had these nice islands. The bright islands there are the TMD layers, and the dark areas is the graphite substrate, which they used. So they grew the material, they looked at it with ARPES. This is electron doped, so that these two pockets, this is the band structure that is predicted. The Fermi level should sit here. They doped with potassium, so the whole thing shifted down below Fermi, so they could see the entire band structure, which matched what was predicted. And then they demonstrated that it's topological by looking at the density of states going from the edge of an island towards the bulk. At the edge of the island, you can see that there's a V-shaped metallic density of state, whereas in the 2D bulk, there is a solid hard band gap of about 60 MeV, and this is the signature of a topological insulator. So this is all well and good, and this is never going to be questioned throughout the following of the talk. What is questioned is the nature of this bulk band gap, because while every topological insulator has a bulk band gap, the band gap of tungsten ditelluride is not just topological, it's actually excitonic. These two works, this graph and this one, come from two different papers which were published in Nature Physics in the same issue, one after the other, because they demonstrated the same thing. This is the work of Professor Ali Yazdani, and this is of Dave Cobden, of course, with their bunch of experimentalists and theoreticians to support. I'm not going to go into detail of all of it, but I'm just going to try to quickly explain to you what's happening here. They are looking not at the topological edge states. They bypass them by grounding them. So they make a device where tungsten ditelluride edges are grounded, and they look at just the conduction in the 2D bulk, pretty much. They look at normal resistivity measurement, so your RXX, and they can see that as they decrease the temperature, the resistance increases dramatically when approaching zero carriers, which tells you that there's a band gap there. That's nothing funky. What is funky is that if you look at the whole resistivity, what you would expect for a normal insulator is for the whole resistivity to diverge at 0 carriers in opposite direction, and instead of diverging, they see something that is sort of flat at every temperature. They explain this by saying that the contribution to resistivity coming from holes and electrons cancel perfectly, because this is indeed an exciton insulator. This is the same message, just reversed. This is resistivity, this is conductance, pretty much the same thing. What do I mean by exciton insulator? In your normal material, in your large gap semiconductor, you have your valence band, your conduction band, electrons and holes, the pairs, we're all happy. In materials where the band gap is very small or non-existing, so for example, in the case of a topological insulator, here the dotted lines mark the edge states, or in the case of a metal, you can have the formation of excitons whose binding energy is actually larger than the band gap existing in the material. So you end up with a band gap that is not given by the fact that there are no available states in the Hamiltonian, but just given by the fact that electrons and holes pair together strongly, that there's no conductivity there. Further proof that tungsten ditelluride is indeed in this state, so going from this towards this, came a bit later in 2024, group of Bentweber. I'm going to try and explain to you this very dense figure. They again grow this material, tungsten ditelluride, via molecular beam epitaxy, on a system that they can gate, so apply a bias to. And they look at the local density of states as a function of the bias applied to your system. So the red curve here is your density state at 0 bias, which is your standard density of states. And you can see that there's a hard band gap of about 60 MeV. So the density of states reaches exactly 0 here. And then they start gating the system. Let's move to this plot, which is much prettier. It's the same plot, just in a heat map. So blue indicates where the band gap is, and then the green, yellowish part is where the states are. So you can see that at 0 bias, you have the band gap, states and states, and then they start gating the system. Normally, when you gate the system and you apply a bias, you have a rigid shift of the band structure, because what you're doing there is just moving the Fermi level up and down. What they observe instead is that when the band gap touches the Fermi level on one end or the other, so positive or negative bias, the band gap collapses. So there's no band gap in the system anymore. And this is because as you gate, what you are doing is introducing carriers, positive or negative. At some point, all of your electrons will be paired up, all of your excitons, will be paired up. No more excitons, no more band gap. So collapsing of the band gap demonstrates that your system is an excitonic insulator state. This is all the premises. There is something that is missing in all of this. As you may know, excitons are bosons. Their bosons are expected to condensate. They want to be together. What was missing was the evidence for a coherent condensate of the boson, a collective mode. Or, in other words, the establishment of an order parameter. Now, if you've never heard what the words order parameter, the order parameter, I told you I was Italian, the order parameter is simply something that is 0 when there is no order in your system, and non-zero when the system is all ordered. It's simply something that tells you the degree of order that you have in your system. Things that you may be more familiar with are the magnetization in ferromagnetism, that tells you how many spins are aligned, or the superconductivity gap, which tells you the strength of the interaction between the Cooper pairs. In this case, we're looking at excitons. So when we look for an order parameter, it can only be in the form of a charge modulation or a spin modulation, because, these are excitons, so there's not that many things that they can do. In particular, there are a bunch of predictions for the ground state of these excitons. And again, this slide is a bit dense. I'm going to try and explain it as clearly as possible. These are theoretical predictions about the ground state of tungsten ditelluride as an excitonic insulator. Let's start from this one here. If we assume that the ground state is in a time reversal symmetry breaking configuration, there are a bunch of different options for charge order. So let's start from this side. This side is very low epsilon to the -1. Epsilon is your dielectric constant, which is inversely proportional to your Coulomb interaction. So low epsilon means high Coulomb interaction. This is low epsilon to the -1. You have a spin density wave phase predicted. And in this case, it's not just a spin density wave phase at these epsilons. It's actually a mixture of a spin and charge density wave combined. So you would have a spin density wave with a given periodicity lambda, and then a charge density wave superimposed on it that has half the periodicity. If we keep moving along the interaction line, we have a trivial quantum spinol insulator state, and then we end up in this spin spiral state. This spin spiral state has no charge density wave associated, whereas the spin are predicted to proceed along the x-axis. In case the ground system is actually in a time reversal symmetry preserving state, the excitonic insulator state is predicted is only one. It's bordered by a metallic phase on one end and then a correlated atomic insulator on the other. And it has a charge density wave associated to it, no spin density wave. And notice that the periodicity of this is double the periodicity of that. So what we wanted to do is try and figure out whether we were in the time reversal symmetry breaking or preserving state, and which order parameter was characterizing our system. To do so, we chose HOPG as a substrate because this would put us here in our phase diagram, which means we would be able to, in theory, spot a charge density wave. And then from the periodicity of the charge density wave, we would know if we were in that case or in this other one. So after a lot of effort, we grew tungsten ditelluride on HOPG. This is your STM image showing you the formation of islands. There's these bright lines here are just step edges on graphite, and you can see that the nucleation of the island starts from the step edges. Let's check that this is actually tungsten ditelluride in the structure we want. We zoom up in atomic resolution image. You can see that there are rows that are bright and dark alternating, which are the chalcogens up and downs that I was mentioning to you at the beginning, so check. The first thing we want to check is that actually we are in a topological insulator configuration. So we look at the density of states going from the edge towards the bulk. At the edge, we see a V-shaped density of state, that's a metal. In the bulk, we see a hard band gap of about 60 MeV, that's an insulator, so that's a topological insulator there, check. We want to check now if we can demonstrate that this is an excitonic insulator. To do that, we look at the density of states in the 2D bulk. So this measurement here is done by excluding the 2 nanometers that are at the edge. We are not looking at the topological insulator state now. And what we do is acquire a series of the IDB, so local density of state maps at every point here, and plot them, which are plotted here as a heat map. Black is where the band gap is, and then purple, orangish is where states are. Of this local density of state map, we take a one-dimensional Fourier transform, which tells us what are the scatterings that are allowed in our system, and sort of allows us to reconstruct the band structure. If you can see, by doing the FFT of this, we find one valence band here. This is the bottom of the conduction band. There's 3 pockets because there's intra-pocket and inter-pocket scattering. Let's not go into the details. But you can see that there's, if you integrate this, there's a hard band gap of 60 MeV. If we now gate the system on one end or the other, the picture looks very different. Let's look at this first. This is positive bias. You can see that the band gap has all but disappeared. Wherever the band gap was, which is where the bands now cross, there's just a dip that is the charge neutrality point, and the Coulomb gap appears at the Fermi level. The opposite, but in the other direction of the Fermi level, happens for negative bias. So this tells us that we can collapse the band gap of the excitonic insulator. So it is indeed an excitonic insulator. So check. Last thing that's left to do is to see if we can see the condensate and the excitonic and the collective modes. Now, if you look at this STM picture here, you can see that this is at the edge of an island. This is a very bright line that corresponds to the topological step edge. But you can see that the density of state oscillates bright and dark, going away from the edge. This would be your signature charge density wave. But it could also be Friedel oscillation or quasi-particle interference or scattering from the edge. Call it whatever you want. And indeed, if you look at the DIDV along this line, you can see that, well, at the edge, there's the V-shaped density of states, and then it becomes a bulk band gap. And then there are these oscillations here, which could be a charge density wave, but also Friedel oscillations. The interesting bit is that if you change the color scale and you go to a log color scale, you can see, maybe, I can see it on my laptop, I don't know if you can see it on the screen, that there are oscillations inside the bulk band gap. There are modulation of the density of state inside the bulk band gap, which means this is not Friedel oscillations, because quasi-particle interference only happens if there's states that you can scatter to and from. To better analyze these in-gap oscillations, we take vertical line cuts in this band gap. So the process thought is the IDV map, log scale, take vertical cuts. And I'm plotting the cuts here. I'm going to move to this other side. every line is a cut inside the band gap, and you can see that there are very clear modulation of the density of states. Note that this is in a log scale, which means that the oscillations are decaying with the same speed of the topological edge, which means that they're imprinted on the topological edge. The interesting bit is if we look at the top, these oscillations have a very, very fixed frequency, which is about 0.29 2 pi over A, where A is one of the lattice constants. So all these oscillations are at the same frequency. The other thing, the other very relevant piece of information that I have to give you is that I mentioned before time reversal symmetry breaking, preserving, blah, blah, blah. The best thing to check this is to apply a magnetic field. This is the measurement done at 0 Tesla, and then we applied a magnetic field of 3 Tesla in the direction perpendicular to the plane, plus 3 Tesla and minus 3 Tesla, and you can see that the oscillation pattern is exactly the same, no matter what the magnetic field is. This is telling you that the symmetry was already broken to begin with. You are not breaking any symmetry here. And in fact, if you compare with theory, the frequency of the oscillations that we see matches pretty well the one that is predicted for the mixed spin density wave, charge density wave phase, which was 0.31 2 pi over A, whereas the one of the time reversal symmetry preserving case lies much further back. Last bit of evidence on this. If you remember, I showed you these maps done by cutting away the 2 nanometer that are at the edge. If you include the edge in the 2D transform, you see in the bulk band gap the appearance of these modes, which are very vertical and very non-dispersive, and these are corresponding, indeed, to the frequency of the charge density wave. So I hope that I've convinced you with this, that the exciton condensate indeed is expected to exhibit another parameter, that we see a charge density wave, and the periodicity tells us which ground state we are in. Now, in the last 2 minutes that I have left, if you remember, I told you that I'm an STM person, but also a photoemission person. Here's proof. We looked at tungsten ditelluride on moly disulfide, and this is because we wanted to see this gap collapse in ARPES. So we thought, if we can make the system collapse in STM, why don't do it like directly? Why don't try and see it with ARPES? So we grow it, and you can see like MOS2 has states here, but there's like a large area where MOS2 doesn't have any density of states. It's a wide band gap. It's the perfect substrate, we thought. So we grow tungsten ditelluride on MOS2, and we thought we'd start putting potassium, which is an electron donor, or F4 TCNQ, which is a molecule which is a non-acceptor, to try and shift this band structure and eventually see something happen in the band structure. Let's look at potassium first. We dope with potassium, and what we see is that the bands of MOS2 shift downwards, which is compatible with the fact that you're adding electrons, so shifting up the Fermi level with respect to the band structure. But then, puzzlingly, the tungsten ditelluride bands go up. And we thought, oh, well, that's because it's closing the gap, maybe. But then we deposited TCNQ, and we see the opposite happen. The bands of MOS2 go upwards, and the band of tungsten ditelluride go downwards, which didn't make any sense to us for a very long time. We scratched our heads a bit until we found 2 papers about the fact that monolayer TMDs can exhibit negative electronic compressibility. This is a lot of fancy words to just say that normally when you add an electron n to your system, your chemical potential mu goes up, so the end mu is positive, normally. But in monolayer MOS2, it's been observed that the opposite can happen, so it can exhibit negative electronic compressibility. Explaining it with a band diagram, you have here the bulk of moly disulfide and the topmost layer of tungsten ditelluride. We will treat for the following: the topmost layer of moly disulfide as an isolated layer, and this is because the van der Waals interaction are very weak. This is the system as we build it. You can see that there's a very small upward band bending of the states of moly disulfide because of sulfur vacancies on the surface. We start putting electrons. You can see that both systems shift downwards with respect to the Fermi level. The band gap of tungsten ditelluride goes fully down, and then there's a strong band bending of MOS2 downwards until we hit a critical doping for which the negative electronic compressibility regime has its onset. Now, the topmost layer of MOS2 just acts as an electron sink. It eats more electron from tungsten disulfide, eats more electron from the bulk of moly disulfide, and it keeps accumulating charges, and basically gives a reduced binding energy for the surrounding layers. And this is to tell you Basically, this is the position of the topmost valence band of tungsten ditelluride and the topmost valence band of molybdenum sulfide. You can see that they have an inverse correlation, so this trend of like the bands getting closer or further away according to the doping is confirmed. Different symbols are different samples grown in different years on different beam times, so this is definitely true. With that, I would like to give you an idea of what I want to do next, because I'm planning to be here for a while. Now I'm looking at strong correlation in TMD layers, which can give rise to this type of phenomena. In the future, I'm interested in looking at edges between this type of structure or other classes of correlated 2D materials. In the very long term, I would be interested to have a knob to tune this epsilon along that phase diagram and hopefully explore phase diagrams of other materials. And in case you're interested, I'll be very happy to have a look at the STM and STS of your 2D materials. Please let them be metallic. And I would love to do some XPS and RPS more, but as I said before, I don't have neither a lamp nor an analyzer. So I'm happy to work on proposal for synchrotron radiation facilities in Spain and abroad. And with that, I'd like to thank you.
Thank you very much, Iolanda. We have some time for questions. Another young researcher.
What is the origin of the V shape when the Fermi level hits the band edge?
Just the collapse of the, so you would have there the collapse of the excitonic state. So the V shape that is left, you're talking about the collapse of the excitonic band gap. It's V-shaped because there's just the Coulomb gap that is formed there because of experimental issues. So when you look at the IDV and you pass by Fermi, if it's a metal, you will have a dip regardless. So it's just an experimental artifact if you want, but it becomes metallic pretty much.
Okay, it's not physical, it's experimental.
It's the charge, it becomes the charge neutrality point pretty much.
Okay, thanks.
Some other question there?
Hi, very nice presentation. So, if understood properly, you used molecular beam epitaxy to grow these tungsten ditelluride layers. So, do you know what is the cause of these islands, the clustering? And actually, also, can you really grow monolayer like this?
So the island type of growth is a Vollmer-Weber type of growth. It's been studied for like decades, to the best of my knowledge. Whenever you try and grow a TMD on a substrate, it will have some nucleation points, and then from there the islands will start expanding. The ratio between the island size is number of island. In other words, how much of a monolayer you have compared to how many clusters you have is dictated by your growth parameters. So there's an entire there's an entire discipline to itself. We tried to get a monolayer as flat as we could, and indeed the RPS measurements that I showed, they had a 97% coverage of monolayers, so only some small islands left here and there. The issue with this specific material is that you basically start nucleating the second layer very quickly before you complete the first one. So it's a matter of fine-tuning your growth so that you can minimize the second layer while expanding the first layer. It's not trivial.
And if you just do the exfoliation, you buy the crystal and
yeah,
have you tried that?
That's what Yazdani and Cobden were doing. The issue with that is that tungsten ditelluride deteriorates in air very quickly, so you have to do it in a PMMA type of environment. You have to seal it. It's not, there's a whole other set of complications. This is because it's not air stable. The topmost layer oxidizes very quickly.
Thank you.
One more question.
Thank you. Nice talk too. The evidence you have about the condensation is this charge density wave. Is there any way to try to get information about the coherence of the condensate?
This is a very interesting question, and this is because the fact that I observe a charge density wave and I call it a collective mode is still under debate. There's still some people that I'm trying to convince that this is actually what I'm observing. I think the first step before demonstrating the coherence of the charge density wave would be to actually check that the spin density wave below exists, and then we can move on to talk about coherence. And then, of course, there's some people that say that there shouldn't be any charge density wave at all. So it's, I think that establishing that it's there for sure is still controversial. Going to coherence would be the second step.
I'm asking because some years ago we have a big problem trying to demonstrate that polaritons were condensating, and it was not accepted until there was proof
of coherence. That's something that I should probably look into. Thank you.
Same question about charge density wave, because now we are studying in chromium, in chromium, there is charge and spin density wave, and we study how it interacts with superconductivity. But it is, in our case, very difficult to get it stable. So do you need thermal treatment? Some people use lateral electric field.
This was just done at 1.2 Kelvin. That's all the magic that we did was putting it into a
So you didn't need any special treatment using external electric field or thermal sighting?
No. It's just we definitely couldn't see it at 4 Kelvin, and it appeared at 1.2. Probably this gives you an indication of how hard it is to stabilize this condensate. So, but the only thing that we really did was to freeze down.
Thank you.
No? Young researcher?
How do you distinguish in your density of states measurement a topological edge state from an edge state due to some surface like TAM or Shockley-like edge states?
I think you don't just use this one technique. So all the DIDV do is they tell you what is the density of state at this specific location, right? So it only tells you if this is metallic and this is insulating, and then you can look, something that can be informative is that speed at which the topological state decays. So the speed at which the V turns into a U. There are some sort of guidelines of how many nanometers this should be. So the length of this decay could tell you something, but I think you need further proof, not just the DIDV.
Okay, thanks.
Last question? No?
Coffee?
Okay, then we close this session. We have coffee now, but we hope to see you back in half an hour for next session.